Let's talk a little bit more about the unit vectors. We've already done some work with the unit vectors and how we can use them to represent other vectors using I and j. Just to refresh your memory, vector I is a unit vector, meaning it has a length of 1, and it goes in the direction of x, meaning that its components will be 1 and 0. Vector j is also a unit vector, meaning it too has a magnitude of 1, but it travels in the y direction, meaning that it has the components 0, 1. And again, this is all for 2 dimensions. We know that we can work with vectors in 3 dimensions. That will come later, so don't worry about that. So for now, this is what we're dealing with. And we know that if you multiply the scalar values of a and b by I and j, the scalar vectors a and b, of course, coming from a vector ab, that these 2 vectors are equal to one another, right? These are different ways in which we can write vectors if we know what their components are. Now, these are unit vectors, but they're not the only unit vectors, right? Not all unit vectors are vertical or horizontal. Unit vectors can go in any direction we want. They can look anything like one of these, for example. So let's say we have a vector, and we're going to say that this vector is vector A, and it has the component form 6, negative 5. And let's say we're interested in finding the unit vector that has the same direction as vector A. How would we do this? Well, if it has the same direction as vector A, then if we're visualizing what this looks like, let's make a little sketch of our xy axes. Vector A probably looks something like this, where we go 6 to the right and down by 5, down to negative 5. That's our vector A. Our unit vector, however, that has the same direction isn't going to have the same length. It's only going to have a fraction of the length, or a fraction of the magnitude of A. So I'll call this the unit vector u. Again, it has the same direction as A, so it will lie atop of vector A, right? They're going to overlap because they have that same direction, but it doesn't have quite the same length. So it only goes so far. Now, how do we figure out what the length of it is? Well, it's a unit vector, so we know that its length is equal to 1, right? So that's good news. But how do we figure out how to represent its x and y components, right? How do we know what the x and y components of that unit vector are, right? We don't know for sure. We know unit vectors have components of 1 and 0, or 0 and 1 when they're perfectly vertical or horizontal. But if they're on an angle like this one is, then how do we know how to figure those out? Good question. What we're going to do first is we're going to figure out what the magnitude of vector A is. And you'll see why in a moment. If we figure out the magnitude of vector A, this is simply the Pythagorean theorem, right? We can use the x and y values, and I know it's negative 5, but it doesn't matter because once we square it, it's going to be positive anyway. So I'm just going to plug in 6 squared plus 5 squared. And if we do this calculation, we should get as a final answer about 7.81. Or if you want to use the exact answer, it would be the square root of 61. Now, why did I have to figure out the magnitude of this? Because if we know the magnitude of the entire vector A, which we now do, and we know the magnitude of vector u, which we do, it's 1, then we know how many times longer A is than u, right? It's this many times longer. It's this many times bigger, right? The magnitude of vector A, or the length of vector A, is this many times longer than the length of the unit vector, because the unit vector is just 1, right? So if it's that many times bigger than that magnitude, then the components will also be that many times bigger than these components, right? It has to be proportional in that way. So if I'm looking at the vector u, its x component is going to be this many times smaller than this x component. So for the x component, I can simply say 6 over the square root of 61. I can divide it. That will make this x component a lot smaller. Same is true for the y component. I can say negative 5 over the square root of 61, just like this. So this will be my unit vector. And if you're not sure, or if you think you maybe made a mistake and you're not sure that these answers are correct, well, we can try, right? We can try to test if these answers make sense. We can see if the magnitude of vector u is truly equal to 1. Because if the magnitude of this is equal to 1, then we did it correctly, because a unit vector should have a magnitude of 1. So how do we test to see the magnitude of this vector? Well, we use our Pythagorean theorem again, right? We do 6 over root 61 squared plus 5 over root 61 squared, right? And we calculate this and we see what we get. I'll show you the actual steps, step by step. If you square this first term, you get 36 over 61. If you square this term, you get 25 over 61, right? Because 6 squared is 36, 5 squared is 25, and then the root of anything squared, you just get that thing, right? So the square root of 61 squared is just 61. Same is true for this one. And when you add these things together, we add the numerators. What's 36 plus 25? Well, that's going to be 61 over 61. Anything divided by itself, that's just going to be 1. So we're doing the square root of 1, which is 1. So the magnitude of the unit vector is in fact 1, meaning that we did this correctly, meaning that the unit vector in its component form is in fact equal to this. And if you wanted to put the approximation, the 7.81, and then divide, or if you just wanted to put this into your calculator and divide it, you would have to round your answer off, but you could see the approximation for what those numbers actually are. And you would see that they are about 7.81 times smaller than these two components. Hopefully that made a lot of sense to you. We can do one more example just to recap all the steps. So example, let's say we have vector b. Vector b can be equal to, I'll just make up some numbers, 7 minus 10. How about that? And I want to find the component form of the unit vector that has the same direction as this. Okay, so we start by finding the magnitude of vector b. That is the square root of 7 squared plus 10 squared. If you do that, you should get the answer 12.21 approximately, and you should use the exact value, the square root of 149, right? 7 squared is 49, 10 squared is 100, so square root of 149. That's the number we should use, right? Not the approximation. Okay, so that means that the unit vector that has the same direction as this is going to be equal to 7 over root 149 and negative 10 over root 149. This is the unit vector in the same direction as this original vector. That's all you have to do.